Now, usually some textbook actually write this as E of reaction. Okay. Just to make sure that this E is a potential difference which may not have a sign, it is just a difference. Okay. But this guy has a sign in the sense that it talks about the reaction going in the spontaneous direction or in the other direction. If it is in the other direction, this guy will be negative, total thing will be positive. So delta G is positive means it's in the other direction. Clear? Okay. So this is just a notation. Okay. Now, if I define it, then actually I can also write, like for example, I know that what is the delta S. Okay. dg is minus sdt plus sdt minus bdt, right? So basically, I have to take the derivative with respect to. We already know this thing, right? What is that? So basically, I am writing del S, right? So del G. If I take the temperature derivative, keeping the pressure constant, right? I should get it, right? So it will be something like, if I just write it, it will be minus N F So the idea is that if I want to know, okay, what is the entropy change associated with an electrochemical reaction, okay, I just have to check that what is the corresponding, okay, EMF change with respect to temperature at constant pressure. But similarly, I could also write the equation for delta H, right? Or delta, say, delta H also I can write, like the way we're writing it, okay. So it is basically delta G plus T delta S.
So it's minus delta S.
This will be a minus S. Yeah. So minus S. Yeah, it will be plus that. Yeah. So what will be delta H? Just straightforward, right? I will just write it as a delta G, right? Plus T delta S. Delta S is this. Delta G also I know. Okay, this is basically minus N F T. Again, E means actually E reaction, okay, plus I'll have T delta S, so basically I'll have N F T. So if I just measure the electromotive force, okay, I can actually derive all the equations, okay, clear. Now similarly, just like we wrote this equation, okay, so remember that there was an equation like delta G. If there is a chemical equilibrium established, it is basically minus RTL and K equilibrium. Okay. So you can also connect it here. Okay. And then we'll get something like RTL and K. Okay. Will be nothing but remember RTL and K was basically delta Z is 0. Okay. Which is nothing but N F is it. Okay. So you can just play with all these things. And what was K? K was basically the reaction quotient, if you remember, where all the species have equilibrium concentration. Okay, we are just coming to that. Okay, where basically the Nernst equation can be easily shown, right? Now the way we have written it, it is basically the delta G of the entire cell. Okay. And then people think that, okay, I can actually think about the delta G of a half cell. Okay. What happens only for the, say, zinc 2 plus? Okay. Now half cell, you cannot actually define again because there is no absolute potential. Okay. It's a potential difference between zinc and the other electrode. Okay, electrode 1 and electrode 2. But if I just think about, okay, its energy is additive. Okay. So then in that sense, I can actually think about, I can trace back, and N multiplied by the electromotive force, that is also additive, right? But you have to be careful, you know that, right? Because you have to always multiply by N, okay? Otherwise, like the zinc equation was basically 2 electron reduction, but the silver was 1 electron reduction, okay? Energies are additive, so N multiplied by electromotive force, that's additive quantity. But we can think then that it is composed of basically 2 electromotive forces, and we can make a like table, right? But then you can never ever, okay, measure the absolute potential. Okay, you can calculate it, we will discuss about it. Okay, but then what we do is that we just measure with respect to another thing. okay, with respect to say any standard electrode. So basically electrode 1 is measured with respect to standard hydrogen electrode, electrode 2 is also measured with respect to the standard hydrogen electrode, and then the difference will be the electromotive force of the cell, that you all know, right? But always the concept is that it is basically potential difference, okay? It's not the absolute potential, okay? But we'll come to it, okay? What do you mean by that, okay? Now, these are all known to you actually, so I'm basically recapping, but just suppose I have a so like I'm just considering a general reaction, okay, and you can take any example, like say for example I have hydrogen, okay, and let's say, yeah. Now usually when I said like I want to actually measure the electromotive force for a reaction, okay, for a half cell reaction, let's say for this thing only. Usually we write it as a oxidation or reduction, whatever. Okay. Now this is actually calibrated with respect to a standard hydrogen electrode, right? Usually, okay, it can be caloric electrode, it can be whatever it is. Okay. So suppose for this thing, I will always have a reversible. Zinc is going to zinc 2 plus. Okay. So I have basically an oxidant zinc 2 plus. Okay. Which is going to basically zinc. I should not write it this way, because as I told you, the convention is always the other way. Right? So I always write it like this. Okay, this is the forward reaction, and then okay, so this is reversible. So this reaction I am presenting like this. Okay. Now this is now coupled with which reaction? The standard hydrogen reaction, right? So basically I have say new H2. Okay, I'll just use notation same, and I have new oxygen. Okay. So not oxygen. This is basically the oxidant species. Okay, oxidized species. Okay. And then of course I'll have the reduced species. Okay. And what happens to this guy? I'll basically have 2H plus for each of the reaction. Okay. But I can actually write it as something like this. Just a minute. H plus. Just one minute. Let me actually use it. So new H2 is basically the stoichiometry of hydrogen, okay, and new H plus is the stoichiometry of H plus. So now for this cell, okay, how do I write the equilibrium constant? Already you know, because I can write the delta G, okay, as some delta J0 plus RTLN, the quotient, that RTLN cube. So for this actually I have the delta G for this reaction, okay, which reaction? This reaction, okay, delta G0 plus RTLN. Now ideally I have to use the activities, right? I cannot actually use the pressure for gas phase, has to be replaced by fugacity. The concentration in the solution phase has to be replaced by the activity, right? So I have to use something like activity of these species, okay? So activity of this, okay, raised to the power, okay? Activity of H plus raised to new H plus, raised to basically the stoichiometric number, okay? And then what I'll have, activity of H2, okay, raised to the power new H2, and activity of this is like oxygen. Now, for the standard hydrogen electrode, we make these two things deliberately to be one, right? Because that was defined that I used basically either 1 atmosphere, or in SI convention I use actually 1 bar pressure, okay? And this thing is basically an acid with unit activity, okay, in aqueous solution. The activity of H plus was 1. So basically I will have ultimately delta G0 plus RT ln AR. Clear? Okay. So ultimately, like I had a cell, I divided into two half cells, but half cells also I cannot measure. Okay, I have to construct a cell. Okay, and then I am actually using a reference. Okay, for each of these half cells, and then I can again go back. This is for a half cell, right? The full cell will be this, and then there will be another one for the other oxidant reductant couple. Okay, like in that case that was basically silver chloride, that couple. Okay, and then I'll have basically two delta G values. This now I have to check which one is the right electrode, which one is the left electrode. Okay, then I will basically take the G delta G right minus delta G left. Okay, that has to be negative. Okay, and then actually I will get the Nernst equation that way. Okay. Now I'm not going, showing you all these things. Okay, already you know this thing. Okay, just and also you know what is the formal potential, right? What is formal potential? If I just actually write it as delta G is minus NFE, already you know. This is, I can write this as minus NFE0. So I'll just divide both sides by minus NF, right? I'll have basically equal to E0 minus RT by NF, right? Some people actually use this minus sign and plus sign and just write it as a O by R. Okay. But then all these activities can be replaced by concentration times the activity coefficient. Okay. So then this activity coefficient term, like meaning I'll have a delta E0 term, okay, and I'll have a ln term of all the gammas, okay, combination of all the gammas. So these together I can call it as something like delta E0 prime, and that we call it as a formal potential. Okay. And then I'll be left to it a logarithmic term of all the concentrations. So I'll get basically a equation which is looks like a standard potential plus the concentration quotient. Okay. But this standard potential now will be dependent on ionic strength, because we know through Debye-Hückel relationship gamma is dependent on ionic strength. Okay. So this is not actually a standard. So that's why we use a E0 prime, okay, and we call it as a formal potential, okay, of the cell. But it's not a very good convention, because the reason is as the reaction is proceeding, suppose, okay, the mass balance is also changing. So the ionic strength will also change, right? So this thing will actually change. But ideally, E0 of a cell should not change because it's a standard, right? So that's why like formal potential we use it, okay, when we write the concentration terms. But strictly speaking, I mean, we should not use it, but we can still approximate if the concentration of the reactants are fairly large, do not change over time, then this guy also will not change too much, okay, over time. Clear? Okay. Now the question is, okay, fine, I already talked about many reference electrodes, okay, and all these reference electrodes, again, let us go back to our this kind of energy level diagram, okay, just to understand what is the reference electrodes, okay, are doing. So I have few examples like let's say, let us start with say standard hydrogen electrode. Or sometimes use in some people write it as a NHE, normal hydrogen electrode. Suppose if I call it as a 0 with respect to that, this is basically 1242. These are all in volts. Okay. And let us take two more couple. One is, let's say, iron couple. Okay. If we usually write it always the reduction way, 3 plus 2 plus. Okay. And then that is 0.77. Okay. And also take something which is negative. Let's take the G1. Okay. 0 G plus G. Okay. So that is 763. Alright, so now this is a relative scale again. Okay. I could have plotted it. Okay. With this guy making 0. So if I make this guy as 0, this will get basically minus 0.242, something like that. Okay. So these are on relative scale. But now the question is there any absolute scale? In the sense that, what are these? These are basically, as I said, like if you think about it, like we were discussing something like we did the platinum electrode, right? And then we are basically applying voltage, okay, which we were discussing yesterday. So that way, if you think, okay, that I have a resistance, all these things we, not resistance, we discussed, right? So I have a voltmeter, okay, and then I also have a some ammeter connected, okay? And then we can actually make some arrangement like this, right? If I apply external bias to it, okay, and then I can actually go to the open circuit voltage. We talked about it, okay, but that, what it means is that the energy levels, okay, I'm tuning, okay, energy level, we will come to it actually, as we are actually biasing an external voltage, okay. Now the question is, what does it mean actually, okay, is you can connect it, okay, to the energy level of these metals, okay, which energy level? It is basically the Fermi energy level. We'll come to it, we'll have a detailed discussion in the next class, okay. Now what will be the Fermi energy level like values for all these metals like zinc, okay, platinum, then silver and all these things, okay. So then if we actually do it in terms of say vacuum values, this will be, these are all again in volts, okay. These are also in volts. So this scale, I wrote it as versus SHE, right? This I wrote as versus saturated carbon electrode. Okay. This is the vacuum value in volt. Okay. This will be something like 5.3. This will be something like 4.7. This will be 4.5. And this will be 3.7. Okay. These are just from electronic structure theory calculation. Okay. Now similarly, one can also ask what is the Fermi energy level of the metal, which is basically the energy level where we get, okay, the basically the electrons are distributed, okay. So if I have the maximum occupation of the electronic energy level, we'll come to it, okay. From the ground state up to a particular state, that particular state's energy level is the Fermi energy level, okay. But of course, that will be the condition at close to 0 Kelvin temperature, because at a finite temperature, you will have electrons also occupying in the higher energy level, okay. And of course, the Fermi energy level will also be dependent on the applied potential, okay. Now, that Fermi energy level, if we write it in terms of the electron volt, it will be something like minus 5.3. It is, all the values are basically negative because it's just a, it's your choice of defining the zero potential. Now you see that there is a direct one-to-one correlation, okay, between the metals energy levels, okay, and the basically electromotive force under standard condition. Okay, that's how we basically made it standard. Now all these like cell standard, like which one you will call it as a standard, okay, that is basically how you are choosing your absolute scale, okay. But the relative scale is not changing because the relative magnitudes are actually connected to the metal's Fermi energy level itself, okay. We are yet to discuss this part, okay, because this will have some more things to introduce, okay. But we'll basically discuss what is the connection between the Fermi energy level and all this. Clear? Okay. Now, again, just to summarize, what we are trying to say here is that, so if we are at the standard state, okay, so then I see that the differences in the electromotive force, okay, can be directly correlated to the Fermi energy levels of the corresponding metals which the electrodes are composed of, okay, clear. But the choice of the standard cell, okay, which is basically cell standard, that is purely arbitrary. I can actually call this as 0, I could have actually called this as 0 also, okay. But it depends actually which electrode is more universal, in the sense like hydrogen people chose at the first place to be 0, But then people found that the calomel electrode is a much more practical electrode in the sense of like it has other technological complication for hydrogen electrode. You know? And there are also many other electrodes. Okay, and we discussed like what will be the conditions for choosing a standard electrode. Like it should not like change its potential over long range. Okay. Usually all these things will happen. Because we said that it is, so basically this part is talking about only how the electron is going back and forth from the solution. Basically how the potential is developed across the interface. But then the question is, it's not only electrons because there are ions also. Okay. And these ions should move around. So the mobility of ion also is important. Okay. There is also another thing called mass transfer, as I told you, that from nearly the electrode surface to the bulk solution. Okay. And there are very like rigorous description also, like in the sense that you can actually use non-equilibrium statistical mechanics to get all this equations. Okay, but we will not do all this formalism. Okay, we'll just restrict ourselves to only the ionic mobility. Assuming that it is in solution and ions are moving, okay, how that movement is connected to the overall conductivity. Okay, because it will depend whether this ion, what is the size of this ion, right? So the cation and anion can actually move at a very different speed, right? And then by the time the cation has reached the negative electrode, the anion may not reach the positive electrode. Okay, and that will create a potential gradient itself within the solution. Okay? So what is the effect of that? All right.